too much. Okay. And again, this list has monatomic and polyatomic ions. The monatomic ions, you can figure out their charge based on where they are in the periodic table, which is why I had to do the dot diagram thing to remind you about valence electrons. And we'll look at this right at the end too if we have time, which we should. What I wanted you to do is to sort things. That's one of the things that scientists love to do, put things into groups, related groups. One of the hardest things for students is all the little details in these chemical formulas. They all, there's a very strict set of rules on how to make them make sense. Okay, remember, capital letters tell you that it's a new element. Lowercase letters go with the capital letters. Subscripts, like this 4 on the ammonium ion, is a count of how many hydrogens you have. And then there's this charge stuff that I've been talking to you about for a while. Okay? So you really have to focus when you look at stuff in chemistry, because every little teeny thing means something specific and it's important. Okay? So yeah, try to work on your focusing skills. I know it's not easy, I understand, especially on a screen all the time. I'm sorry. All right. So you were supposed to, and actually I should pull this one off too. You were supposed to look at this list and then put the ions into boxes that had the same charge. I know I rushed it at the end of class on Tuesday, so I apologize, but let's do it nice and slow, okay? Hydrogen, oh, I know what else I wanted to do. And of course the heater. All right. So hydrogen's H plus hydrogen, right? You write the symbol, the charge, the name, all done. Okay, go down the list. NH4. That means 1 nitrogen and 4 hydrogen atoms are stuck together to make a polyatomic ion. So this is not going to go on the monatomic ions. We're going to come back to ammonia. We're going to talk about it today, but not now. So then we did hydrogen, and then we're just going to march. Well, you guys probably can't see me, but we're going to march right through the important alkali metals. Lithium. This we're supposed to type in Li. And then do control period for superscripts. Control period to get out of it. And lithium. Next on the list, sodium. Big N, little a. Control period. Positive. Get out of it. Control period. Sodium. That's all you were doing here, is putting all the plus ones, which they don't have a 1, because you don't have to write 1 if you write the plus sign. Okay. And then there was mercury and copper, and I said don't do mercury because it's weird. Okay. So down here at the bottom, I told you also not to do anything with these. I'm just going to go to the next page. Mercury. There's 2 mercury atoms that stay together, that have each lost a single electron. What just happened here? Sorry. They've each lost a single electron, but they're like the diatomic elements. Okay, they stay with each other. Each of them lost 1, so they together have lost 2 electrons. That's the +2 charge. Okay, so what I'm going to write here are the stock, oops, that's not the right one. The stock names: mercury, Roman numeral 1, That tells you it's lost 1 electron. And then mercury, the next one below it, is Roman numeral 2. Unfortunately, or fortunately, they have the same charge, but there's this subscript thing on the other one. So let me go back up here. So now I'm in the +2 box, and I'm going to write Hg. Remember, mercury's ancient name is hydrogyrum. Okay, crazy stuff. Do control comma, and you get a subscript 2. Control comma to get out of that, and then control period to get a superscript. A little bit complicated. Okay. And then do a 2 plus. Okay. Get rid of the superscript and go over. This is mercury 1. 2 atoms of mercury that have each lost 1 electron that hang out together. And then mercury 2 has the same charge, and it's a single atom that's lost 2 electrons. Now, I'm not going to test you on mercury. Maybe I'll make an extra credit at some point, but probably not. College professors love to throw this one in there because it's so wonky. I don't know why they always focus on the exceptions, but I want to introduce it to you because you might see it again if you have to take chemistry again. Right? So remember from yesterday, our discussion, the OUS ending indicates the fewer number of electrons lost. The IC ending indicates a greater number of electrons lost. Because mercury's name is so wackadoodle, we don't use its ancient name. Remember, with copper and iron, we use their Latin names. Mercury, they didn't even bother to change it. So we go mercurus and mercuric. And so which one's which? Go back up here and make it easy on yourself. Once you've done it once, you can just copy. Okay, and come back here and paste. And I'm going to cheat just a little bit and paste it again, but I have to take out this subscript. Okay, so mercurus and mercuric. It's a lot easier to remember if you go mercury 1 and mercury 2. Okay. The next one on the list is copper, and again, you do need to know the 2 possible charges for copper, +1 or +2. So copper 1 is going to go up here. I'm skipping right and all the other ones, so there are other ones that are supposed to go here. I'm just going to skip down copper. One, and then down here, and I could cheat again. Here, watch this. Do this, and then 2 right there, and put 2 Roman numerals. Okay, so there's copper 2. Okay, and then we'll go down to this new list. This is the part that I told you not to do last time, but we do need to know it. Copper 1, copper 2. Let's do that. And then I'm going to get rid of the space, and I'm going to do the right name. So remember, copper's old name is cuprum. So this is going to be cuprous. And again, save myself some typing. And this is going to be a 2, and this is going to be cup. Right, and then you just march yourself on through. The next ones are all +2s because they're all the alkaline earth metals. Right, so you don't write a Roman numeral for magnesium. because it only ever has a +2 charge. It never changes. So you don't write anything more than you absolutely have to be clear. Okay? A lot of times when you learn something new, people want to start using it with everything. It's not necessary to write the Roman numerals because magnesium only ever forms a +2 charge. Same with calcium, same with strontium, same with barium. Zinc's a little bit weird. I'll talk about that in a few minutes. Zinc is a transition metal, but it only ever has a +2 charge. So those would all go underneath magnesium. And then we've got tin and iron. So come down here. Tin can be a 2, and tin can be a 4. Remember, IV is for 4 in Roman numerals. Tin's old name is stannum, so this is going to be stannus. This is going to be stannic. Okay. And so SN 2 plus stannus. Cheat again. It's not all of it. It's not really cheating, it's just being smart, right? Okay, and then iron 2 and 3. You absolutely have to know that. And gold is a transition metal, and it almost always has a +3 charge, so we don't generally put in the other forms of it. Lead is the last one that you have to include in this bottom box. And lead is like tin, they're in the same family. Lead can form a +2 or a +4 ion, and I'll explain that later. So ferrous and ferric, plumbous and plumbic. It's weird, but those are their names. So that's what you were supposed to do here. There's only a couple, you know, in the +4 and tin and lead, and then the +3 was gold and aluminum. And I think that's all of them. So I didn't fill them all in, so forgive me, but that's what I was asking you to do. So next week, we're going to do something similar, but we're going to sort out the polyatomic ions, and they're trickier for sure. Notice that the first column on this list are all cations, they're all positive up until here at hydronium. Okay? And then all the remaining ions all have negative charges. 1, -2, there's a couple of -3s. Most of them are -1s and -2s. And then 1 -4 silicate. Okay. Now, another thing I want you to notice about these, because we're going to talk about these polyatomic ions today, is in addition to almost all of them, there's just 2 that are positive, ammonium and hydronium. All the rest are anions. They all have extra electrons. And also, if you look at the letters, all the capital letters, fluorate, chlorate, chlorite, bromate, bromite, nitrate, nitrite, manganate, what the heck is that? Iodate, sulfate, sulfite. Look at all of these. What element do they all have? Except for this one. They all have oxygen. Okay, that's a big deal, and we'll be talking more about that. Questions about the monatomic ion search? Was that helpful going over that? Or sort, not search. Any questions? Anybody alive out there? Everybody's good. I can't see the chat. Everybody's good? right, I'm moving on then. So the next thing I'm going to do is close this and go back to the PowerPoint. So I believe I will disappear from your screen, which probably isn't a problem for most of you. Good riddance, right? Okay, here we go. So this is where we left off yesterday. Talking about copper. Again, the lower charge, the fewest electrons lost is OUS ending suffix. And the greater the number of electrons lost is thick. Again, copper 1, copper 2 is a lot easier than trying to keep this straight. You don't have to remember if it's a +1 or a +2 or a +2 or a +3 or a 2 or a 4. Okay, it's a lot less confusing. So we've gone over this. This is from your textbook. They have a whole list of all the, well, it's not all. It's not even close to all. They have a list of a lot of the common polyatomic ions. Then these are the ones with more than one charge. And I'm going to tell you there's more than these. This is just some of the important ones. The ones I want you to remember for sure, absolutely have to know: copper and iron. And then I would also like you to, I will probably have something with tin and lead when we get to compounds later. But the stuff with mercury, meh. Okay, don't worry about that. Chromium, it might be an example, but I'm not going to test you on knowing it. But again, we're always going to use the Roman numerals. You're not going to have to worry about the us and ich stuff. So you should be able to figure it out. Okay? Just know that if it lives in the middle of the periodic table, there's a chance that it might have a variable charge, high chance. So let's talk about what's going on with tin and lead. I thought I'd just throw this in there because they do something weird. So tin's on the 5th period. It's in carbon's family. Both of these are in carbon's family. So remember, carbon's a non-metal, and then we have silicon and germanium that are metalloids, and then below it, as you go down through the family, is tin. How many valence electrons does tin have? 2 plus 2, S2P2. It has 4 valence electrons. So it shouldn't be surprising that it forms a +4 charge. Okay, common, that makes sense. Lead, well, so does it make sense? So carbon's small enough to hang on to its electrons, but not big enough to get anybody else's. Same kind of thing with silicon and germanium. They share their electrons. We talked about that yesterday. They form covalent bonds. Tin and lead have layer after layer after layer after layer after layer in their onions. Okay, and so those electrons are far away from that positive nucleus that's trying to hold on to them. There's all the repulsion from the shielding going on. So the turns out, if you recall again, the S's and the D's are really close in energy, right? The little stuff with the copper's S electron moving back and forth. Turns out that sometimes it only loses the P ones, the farthest away ones, which is why it has this 2 and 4. Lead, of course, is even bigger than tin. It has even more layers, but it follows the same pattern. 2s and 2 in the P has 4 valence electrons. It will form a +4 charge, and also sometimes it forms that +2 charge. So I just wanted to run through that. I think it's a good So even though they're not transition metals, they can have a variable charge. Pipe in if you have a question. Okay, feel free. All right, so what would we call it? Well, stannum is its old name. So the least number of electrons lost is STANS, and then stannic. Is the old name for lead. Wombus, wombic. do some review next week. This is another document that is in your classwork area, and it is a reference material. This is probably a paper that you would want to print and have. If you have to take chemistry in college, it would be a good one to have. However, a lot of the information on this is, I don't know, redundant, right? Once you understand about valence electrons, knowing the position, knowing that everybody in group 1 has 1 valence electron and everybody forms a +1 ion, everybody in group 2 has 2 and they always lose them. Everybody in group 13, well, for our purposes, group 13, they have 3 valence electrons and lose them. Carbon's family is all mixed up, like I just said. Everybody, but they have 4 valence electrons. Everybody in group 15 has 5 valence electrons. They just need 3 more electrons. Okay, so they get a -3 charge to get their octet. You have 6, you need 2 more electrons. If you have 7, you need 1 more electron. Of course, if you're a noble gas, you don't need any more electrons. Okay, you don't form ions. But so, you know, having all the symbols with their charges, that's not that helpful for those. It's very helpful for the elements in the middle. And a couple that I want to point out to you that we will be using frequently. Zinc, even though it's a transition metal, it only ever loses its 4s electrons. It's all full, right? This is D10, has all of its d electrons. It only ever loses its s. Silver is D9, and so if it gets 1 more, it gets a full d orbital string, and so it only loses 1. Right? So that's really important. And again, copper, iron, you've got to know that those form 2 different ions. And where the heck are those 10 left? About everything. All right, so again, monatomic is 1 single atom or 1 type of atom, and polyatomic means there's multiple atoms. So when you look at an ion's formula, these little subscripts tell you that there's more than 1. So nitrate is nitrogen with 1, 2, 3 oxygen. So rather than write the oxygens 3 times, we write oxygen once and put the 3 here. Because it has a negative charge. So the book talks about common anions because there are so many of them. Okay. C2H3O2 looks crazy, but that's instead of writing CCHHHOO, right? It makes it more compact. It's our little secret code inside it. There are only 2 polyatomic cations. The first one is the one you absolutely have to know right now. The second one is one we'll talk about later when we get to acids and bases. So ammonium is NH4, and it has a +1 charge. This isn't typed out very well. Hydronium is H3O, not H2O, and it has a positive charge. It's missing 1 electron, so is ammonium. So let's do a little preview on dot diagrams. Nitrogen, group 15 or 5A, that means it has 5 valence electrons. Has a lone pair on one side. I always put it at the top. It doesn't matter if you started it on the left or the right, but one of the sides has 2 electrons in an atom. If you recall, I think I talked to you about ammonia. Ammonia is a gas at room temperature, and it is not charged. It's a compound. Okay? When you percolate this gas through water, it makes ammonium and another ion called hydroxide, which we don't need to talk about just yet, but I just want to point that out. What happens is hydrogen ion, which is just a proton, which means it's positive, clunks itself, attaches itself, is attracted to that lone pair. Okay? That ends up making a positively charged polyatomic ion. Instead of writing NHHHH, you write N4 with a plus 1 charge. Right, again, that's the only one. Ammonium. All the others are anions. Okay? So, again, this is really small. I apologize, but we just looked at this. We go through this list. These are all monatomic in the first column except for ammonium. And then here's hydronium, the other positive polyatomic. And starting here, with hydroxide, these are all anions, are all negatively charged. So you'll see pictures of representations of molecules and ions in your book. Nitrogen is typically blue, sulfur is yellow, oxygen is red in color coding for chemistry. So the polyatomics have more than one atom. Okay? It's not just a sodium atom that lost an electron. It's multiple atoms that stick together that have a net charge. Okay? Nitrate has nitrogen and 3 oxygens, and the charge is a -1. Phosphate is a phosphorus with 4 oxygens. Sulfur is a sulfur atom with 4 oxygens. Notice that the charge, and so that gets confusing. And I'm going to try and give you a trick on how to keep it straight. But not until next week. Okay, so again, polyatomics are essentially almost, they're, I can't say all, almost all are just non-metals stuck together. Almost all of them have oxygen, and almost all of them are anions. Okay, and they also end with either ite or ate. So like we just learned about us and ick, it's kind of the same thing but different. So the ITE ending means a fewer number of oxygens. So this is sulfur, 1, 2, 3 oxygens. That's the sulfite for sulfur, and ITE, fewer oxygens. It has a -2 charge. There's also sulfur with 4 oxygens. It also has a -2 charge, but this time we call it sulfate. Okay, so ite means fewer oxygens, 8 more. Has more oxygens. It's a dumb way to remember it, but it works for me. Okay, the cool thing is they're always negative. The cool thing is they both have the same numeric charge. Only thing that changes is the number of oxygens. There's all sorts of them, like I was saying before, nitrite, nitrate, sulfite, sulfate, phosphite, phosphate. It's all mixed up. Seems impossible to figure out, but I'm going to give you a tool for the most important ones. So 3 oxygens, 2 oxygens. This is nitrate, this is nitrite. 4 oxygens, 3 oxygens. Phosphate, phosphite. So these numbers, the numbers of oxygens aren't indicated exactly with the endings. It just tells you which one has more. All right, the last one before I flash up the dot diagrams, chlorine. Okay, so we got these pairs that have different numbers of oxygens. Turns out there's several sets that have 4 different permutations with oxygen. So chlorate has 3 oxygens. And again, we're writing this instead of writing OOO. Okay? -1 charge means 1 extra electron. Chlorite will have 1 less, ClOO, which of course we won't write. We'll write ClO 2. Remember, this is an L. I try to make a cursive L because it's confusing whether that's a carbon and an iodine. It's a lowercase L for chlorine. Okay. Forgot to mention that earlier. Now, here's the wackadoodle thing. There can be chlorine with 4 oxygens. What the heck? Well, I can't call it chlorate because it already is taken. So then we have to add on a prefix. And per is added on. So it's perchlorate. It's chlorate with 1 more. And just to make it actually extra annoying, there's actually chlorine with 1 oxygen. Chlorites are already taken, so we have to add a different prefix, hypo. So you guys are familiar with hyper, like hyperactive, overactive. Hypo means under. Okay, less active, for example, like a thyroid. So hypochlorite. So they're all chlorine, they all have oxygen, 1, 2, 3, 4 of them. They all have the same -1 charge. It's just the number of chlorines changed, so they all have to have their own name. Sodium hypochlorite is used in pools and spas and hot tubs. You also may be familiar with sodium hypochlorite as bleach. So sodium forms a positive ion, hypochlorite has a negative, right? The electron from sodium goes to this one. They go into water, they dissociate the ionic compound for you. Sodium hydrogen carbonate, NaH, and carbonate CO3. This is also called the bicarbonate ion. I don't know why, because somebody made it up a long time ago, but you know it as baking soda. And this is actually a picture of Alka-Seltzer tablets, and so the citric acid, right, baking soda and vinegar. You guys probably know about volcanoes from back in the day. That releases the carbonate, the carbon dioxide bubbles. So this is baking soda with citric acid in those tablets. All of these ions, a lot of these ions are important for keeping your electrolytes balanced in your bloodstream and your body, keeping you functional. Hydrogen phosphate and dihydrogen phosphate is also used for fertilizers because plants need phosphorus, among other things, which is an example. All right, we'll get to Nick the Camel on today. So I have used up almost all of our time, so I'm going to ask if there's any questions. I got a little carried away with my talking for this period. I'm going to stop recording. Anybody have any questions right now?